Hello everybody, my name is Mirzobek Malikov and I'm pursuing a master's degree in aerospace engineering. Today I'm gonna discuss incremental nonlinear dynamic inversion control method, or simply INDI. As we know, aircraft don't always behave like linear systems. In some flight regimes or in some failure scenarios, they behave in a nonlinear way. To control them, you therefore also need a nonlinear controller. And this controller should be as robust as possible for the model never exactly matched reality. In this sense, the nonlinear dynamic inversion control (NDI) has proven to be an easy way of controlling nonlinear systems. However, an aircraft can be very complicated and NDI requires the model of the system has to be known quite accurately. In this case, a possible solution is offered by incremental NDI. The INDI incremental NDI is a sensor-based control method which requires less model information in both qualitative and quantitative sense. This improving the system robustness against model uncertainties. So today, here I select this paper from the Journal of Guidance, Control and Dynamics. The topic is Stability Analysis for Incremental Nonlinear Dynamic Inversion, INDI Control. Our authors are from China and Netherlands. Their affiliations are Delft University of Technology, Netherlands, and Hong Kong Polytechnic University, China. Publication date is 5th of May 2019. Here we should mention the previous research papers which are relevant to our chosen paper. It was mentioned that despite the numerically verified robustness of INDI to aerodynamic model uncertainties and disturbances, its previous theoretical stability and robustness proofs have some drawbacks. These previous attempts drew the stability conclusions based on the linear transfer functions derived from block diagrams where inappropriate assumptions are made. The influences of disturbances and uncertainties on the internal dynamic also remain unknown in the literatures. Here is our paper. In this paper, the INDI control from the literature is reformulated for systems with arbitrary relative degrees without applying the time scale separation principle. The reformulated INDI's stability and robustness are then analyzed using Lyapunov-based methods. Finally, the reformulated INDI is compared to the NDI while taking into account model uncertainties and external disturbances. Here we start from reformulation of INDIs. In the paper, the researchers have taken three problems into care: input-output linearization, output tracking, and input state linearization. Here we make focus on mostly on input-output linearization. It was mentioned that MIMO system, as we know, the MIMO is multi-input, multi-output system, and we have the state space equations. And in this case, it was assumed that number of inputs and the number of outputs are same. So the P is equal to M. And also we should take care that H was denoted as HI, which is some vector, has m elements, and G is originally is matrix, but its column vector, it was denoted as small g, and it also has m elements. Then Lie derivative is defined. So here we have the formulas. So as we know from the explanation, the Lie derivatives of the function h with respect to the vector fields f and g are defined as these formulas. Then output dynamics of the system can be represented as this matrix form or just in equation like this form. After that, in the paper, smooth function also defined, and z transformation function also defined, and here we have two nu and xi, which are the state vectors for internal and external dynamics. So our nonlinear system described as using these equations, and our NDI control input is u equal to beta minus I x v minus alpha x. However, here we have NDI system is reformulated. However, the NDI linearization is based on the exact mathematical cancellation of the nonlinear terms alpha x and beta x. That is almost impossible in practice due to model simplifications, computational errors, and external disturbances. And here, in this case, we need to have some different way to get some good equations. So in this case, here, INDI will come to reduce the model dependency. In the next page, we can see that incremental NDI is calculated. First, we need to take the first order Taylor expansion series from our original equation, and after that our system becomes like that. So this is INDI case. Need to mention here we have perturbation term, and after that our INDI control input is defined like that: u equal delta u equal to beta minus v minus y, that output. Here we don't see our model. I mean alpha x and beta x is we don't see, and we can see as compared to the conventional NDI control law, the INDI control method is less sensitive to model mismatches because alpha x is not used in the equation here. On the other hand, INDI control method requires the measurement or estimation of y, the output, and the actuator position u0. This is why INDI is referred to as sensor-based approach, so the model dependency is reduced. Now we can see this. That's why we can see the perturbation terms here. In the paper, the stability analysis was discovered. So the stability of the INDI at the origin z equal to 0 of closed loop system is analyzed. To check the ability to check the stability, the actuators are assumed as ideal and perfect sensing. Let's consider the following system as the nominal system. Here we have equations, and we have two lemmas. The first lemma is the origin of the equation is asymptotically stable if the origin of nu dot is asymptotically stable. In that case, nu dot is referred to as the zero dynamics. And the second lemma is the origin of the equation is globally asymptotically stable if the system nu dot is input to state stable. And let's assume the partial derivatives of alpha and beta with respect to x up to any order are bounded. So which means in when the sample delta time goes to 0, our norm of delta x becomes 0. Then the perturbation term satisfies this case, so which means the sample time, as sample time goes to 0, the norm of perturbation term becomes 0, and finally that delta t guarantees the boundedness of our perturbation term, which means that the norm values of this perturbation term becomes negligible for sufficiently high sampling frequencies. Also, this bound can be further diminished by increasing the sampling frequencies. In our next page, we have one theorem. If perturbation term is bounded in this less than delta epsilon is satisfied for all z, and our state nu dot is input to state stable, then the state z of our original equation is globally ultimately bounded by a class k function of delta epsilon hat. So it is proved by applying Lyapunov's method in the paper. So it was chosen the Lyapunov method as like that. Xi transpose P Xi. So in this case, clearly we can see that V is a positive definite function, and the time derivative of the Lyapunov candidate was also negative semi-definite function. Here we can see. So in the next page, by the definition of the input to state stability, there exists a class KL function beta 0 and a class K function. The internal state nu satisfies this inequality, and as the beta 0 belongs to class KL functions, so our z satisfies also this inequality, which proves that the state z is globally ultimately bounded by class K function of delta. About robustness analysis, the robustness analysis was also considered in this research. As we know that INDI has promising disturbance rejection ability. It has been proven here in this research work, but now I'm not going to discuss it so deeply. And according to the analysis in the paper, INDI control has shown promising inherent robustness to disturbances and regular perturbations without using any additional robust or adaptive control technique. So in our next page is numerical validations from the paper is we can see. So in this paper, rigid aircraft gust load elevation GLA problem is considered. So the velocity of aircraft VF angular velocity of aircraft was denoted as sigma. Then control input was U. So here we have the picture of turbulence field. The picture is from originated from the paper itself. Then also Simulink blocks design also. It's also from our paper. Here we can see the graphs. So let's have a look at some results given in the paper. The first is about command tracking control in turbulence field. it was considered that output tracking problem was considered as y. Here we have the vz is our velocity along z axis, and the pq are our angular velocities. If you look at the first graph from the left, it's for vz velocity. Here we have a reference. We should make a look first here. It was mentioned that NDI is blue color line, and INDI is dashed red colored. And the reference, we have a reference, so which means that INDI and NDI tries to reach that reference. And if you look at it to the first graph, our reference is located between 9 and 8.8, and it can be clearly seen that INDI makes better result than NDI, because NDI is a bit far away from the reference, and the INDI is more closer. And if you look at the second graph, it can be seen that NDI and INDI makes so close, so similar results, but however, there's some in the downwards there are some differences we can see clearly, and also in this case also the INDI makes better results. In the fourth one also similar. I mean, in the third and fourth also INDI perfectly clearly can be seen that gives better than NDI control system. Here we have the error tracking controls. As we know that for error tracking control, our error goes to 0. We want that our error goes to 0. So NDI and INDI graphs here, if you look at the first graph, INDI error is more closer to 0 than NDI's. In the second and the third graphs also gives almost the same, which means that INDI more closer to 0, INDI is 0. So, but the fourth one is a bit challenging. But however, if we look more carefully, that we can see that INDI in this case also tries to be more near to 0 than NDI control. Here we have actuator dynamics and limits are considered in this validation. So this in these figures shows that control inputs where INDI's responses more actively for elevating the turbulence influences. Moreover, the control surface deflection angles are within the limits under both NDI and INDI. If we look at the limits, so for aileron, elevator and rotors are plus minus 35, plus minus 25 degrees respectively. And if you look at the each graph carefully, both NDI and INDI are between that ranges, between their limits. In this case, we have control inputs with model uncertainties. So now we are looking at model uncertainties. In that case also, INDI and both of them are between that limits, plus minus 35 and plus minus 25 respectively. And here comes our conclusion. So this study reformed and generalized the INDI control for systems with arbitrary relative degrees. The state of the closed loop system is demonstrated to be eventually constrained by a class K function of the perturbation bounds using Lyapunov methods and nonlinear perturbation theory. Without utilizing any additional robust or adaptive methods, it is demonstrated that INDI is more robust to regular perturbations than nonlinear dynamic inversion (NDI). Additionally, it can withstand certain singular disturbance regions. Furthermore, the simulations showed how well the reformed INDI control worked. Thanks for your attention.